All right, our journal today is a simple spring attached to a block on a surface. And this is right out of an AP Physics C prep review. And it's a little confusing what they mean by x equals 0 and then x equals x naught. Like at first glance, that looks like it might just be the same thing. So let's see what it says. The mass is moving to the right with a velocity of something bigger than 0. No. It has a velocity initial at the position x equals x naught. So here we go. Neglect friction. The spring has a force constant K. What is the total mechanical energy of the block at this position? All right, so here's what we have to understand about the way the author set up this problem. This boundary right here is equilibrium for the system. This is equilibrium for the system, and they're saying that that is an x of a position 0. They're saying that the block isn't here, the block is here. So they're saying that you can conduct the experiment, or you can conduct whatever you want to do visually here, by assuming that we are at some position, an initial position, an x initial position. So this is x other, in their opinion. So we're saying you literally are here, and here is the initial position of where you picked it up, and that position is not at equilibrium, and that position means it is moving here. It's moving to the right. So from here, it's moving to the right, from there with some unknown velocity at this position. Geesh. That's just, I don't know why they chose to use that verbiage. To me, it seems a little confusing, but nonetheless, here we go. So then it's asking you, the spring has a force constant K. That's great. That gives it energy. What is the total mechanical energy of the block at this position? And it's really important that it's asking you, what is the total mechanical energy? All right. What is the total mechanical energy? And for this, I am just going to go up to the top of the screen. Ben, what is your best guess on this? Do you think it's A, B, C, D, or E? What's your best guess on this?
B.
Hey, I like what you're thinking. Ben says it's 1/2 mv squared plus 1/2 kx squared. Absolutely it is. So nice job. And I think, if I were answering this question, wow, I just made it much smaller, didn't I? If I was answering this question right here, I might be obligated to think about it this way. Yesterday we did bar graphs. And if we look at bar graphs kind of help us with the mechanical energy that occurs initially, and we compare it to the mechanical energy that occurs in a final scenario, like this. And if we're thinking about it that way, we can think that in an initial sense, it doesn't even tell us what we have initially. It only lets us know that there must have been some kind of energy that occurred initial. So I'm going to put this outside here, and I'm going to say that initially I know that I have this kind of an energy, and that kind of an energy right there would just kind of represent an energy that would be total to this system that begins right here. So I'm going to hook it up like this, energy total. Then as I come over to here, and I don't know what Ben did in his mind, but in his mind, he kind of looked at it this way, that no matter what it was in the beginning, we know that over here in our final scenario, it looks like It's a combination of these two. And whether they're half and half makes no difference to us. We just know that in the final scenario, we know that it's moving, so it has to have some kinetic energy. And then we know that that spring is getting stretched out, so there's got to be some elastic potential energy also in that scenario. So once again, what I want to show you is that the way to solve these, I think, in your brain is to think about these things as bar charts. Because the question is really specific, isn't it? It doesn't say, what is the kinetic energy of the block at this position right here? It doesn't say, what is the elastic potential energy of this position? It says, what is the total mechanical energy of the block at that position? Well, we know the total mechanical energy has to equal all the initial mechanical energy, whatever gave it that energy, because it doesn't tell us. And we know that the total will be made up of this. So that's where my mind goes doing these problems. And I hope that is a satisfactory solution for all of y'all's out there. Now what I'd like for you to do is I want you to open the week 19 folder. We're going to do a lab today. And I'm going to Castify that too. So let me shut down the Castify here. And we're going to do this lab as a cami. And I know that isn't like the favorite way to do this lab. I mean, naturally, I'm always willing to let you do this lab on paper. I just think this lab is going to be easy enough. We can do it as a cami. So I invite you to try it that way. If you know you're somebody that in general is like, ick, I don't like to. I think you're going to enjoy this one. So let me stop doing what